Now we're going to look at the sum of the forces in which direction? Sum of the forces in the parallel direction is equal to mass times acceleration parallel. Aha! And by the way, that's really what we're solving for. We're solving for acceleration parallel to the ramp. Those two little lines, it's not acceleration 11, it's acceleration parallel. Everyone okay with that? I really don't care what symbol you use. I'm not sure what your textbook uses. Sometimes they call it A1, A2, but I like to just call it perpendicular parallel. It's just easier to understand. So now, what works in the parallel direction? I'm going to highlight this in, is this cyan? What's working in the parallel direction? We got the force of friction trying to slow you down. That's the whole point of designing a half pipe, so that when a skater wipes out, they can slide on their knee pads and not get hurt. And then what else is acting parallel? What's pulling you down the incline? Gravity. Weight, but which weight? It's weight parallel. Aha, you see that? And since we're going down, weight parallel we're going to call positive. We're going to call going down the incline. Here's our frame of reference. We tilted our head, right? Instead of calling this x and y, it's perpendicular and parallel. And we're going to call going down the incline positive, going up the incline negative, being pushed up the incline positive, being sucked down onto it negative, right? Just for a frame of reference, which is easy to mess up. So in the parallel direction, we have weight parallel minus the force of friction is equal to mass times acceleration parallel. Woohoo! The end is in sight. We can get there. Weight parallel is 653.5 newtons is pulling you down that hill. Force of friction. Can we find the force of friction? Yay! Force of friction is what? Fun, right? And in this case, we set the coefficient of kinetic friction to be 0.15. Which I was trying to look up on skater websites, but of course, most skater websites are going to say, dude, the coefficient of friction of my plastic knee pads on a wooden incline is 0.15. Yeah, not at all. So anyway, force of friction is equal to 0.15. And then you tell me, what do I use for the normal force? Is the normal force equal to Tony Hawk's weight, 754.6, or the weight perpendicular? Which one? It's equal to the weight perpendicular, which is 377.3 newtons, yeah? You see that? So the force of friction is actually less because we're on a hill. The hill is tilted. There's less contact between the ground and the knee pads. Think of it that way, right? So I take 0.15, 15% friction of the normal force, 377.3, which is how much the ground is pushing up into the knee pads, right? And I get about 56.595. We'll round that off at the end. 56.595 newtons for friction. So I'm going to subtract that from the weight parallel force, and that's the force that accelerates you down the incline, is equal to mass times acceleration. And we know mass is 77 kilograms for Mr. Hawk. Now we can find out how much he's going to fly down that ramp, how much he's going to accelerate. Whew, we're almost there. Are you tired? You're allowed to be tired. So we're going to take 653.5. That's the weight parallel down the incline. Subtract the force of friction, which is 56.595. And then how do we get acceleration parallel by itself? Divide both sides by what? By 77 kilograms. And we finally get an acceleration of 7.752. Good enough. Units for acceleration. Meters per second. And if you think about it, let's use a little common sense. Is it common sense that if you're sliding down a half pipe on your knees, you're not going to be going faster than gravity? What's gravity? 9 point what? 9.8, right? Yeah, in fact, the acceleration should always be on a half pipe less than 9.8 because you're using gravity to your advantage, but you're using the ramp to water down gravity is the way to think of it. So in real life, this could be a type of calculation somebody would do when they're designing a half pipe. My guess is they don't do exactly this. There's probably a lot of art to it. And the half pipe is actually complicated. It's not a constant ramp. It changes. It tapers off. It's crazy. But here's what I do want to show you. This is actually really cool. I had a student who's, I know this sounds like I made this up, but I didn't, whose dad was a lawyer. And there was a lawsuit. Okay, this is a real-world physics document. It's kind of cool, where this worker got injured moving a 630-pound, I think it was a refrigerator, up a ramp. And there was an accident where it fell over and hurt the guy, which isn't cool. And there was some kind of lawsuit going on with the angle of the ramp, the weight of the object, the friction, and all that. So it's kind of interesting that they actually had to hire a physicist, an engineer, mechanical engineer, a scientist to kind of help break down all the forces that were involved there to see who was really at fault and all that. But in the end, the goal is to not kill somebody, right? To actually understand. So in a nutshell, let's kind of summarize what we just did. It's actually just one little trick. And the trick is, instead of thinking of x and y because this is hard to think about in terms of x and y, rather, right? We don't use an x and y reference frame. We tilt our head and we think of what? We think of perpendicular and parallel as our reference frame. And then it makes it a lot easier because now the skater isn't moving in x and y. The skater is just moving in the parallel direction. And in a nutshell, then, we can use Newton's second law to find the sum of the forces perpendicular and parallel to determine his final acceleration down that ramp. And there you have it.